pleasure to host this event for you. This is an event dedicated to EuroHPC systems, but from the point of view of AI and AI use. My name is Lilith Axner, and I am a program officer at EuroHPC Joint Undertaking, responsible for infrastructures, working at the infrastructure team. And with me, I have two more colleagues. And with great pleasure also going to introduce you our hosting entities and the users of our systems that will present all the tips and tricks that they have applied to successfully use EuroHPC systems during this event. The event will be recorded. The recording will be available on our channels, and you will be able to post your questions through the chats, but you will not be able to unmute and talk. So we will have question and answers sessions at the end, and also if time permits, then we will try to open the question and answer possibility also during the breaks. But you are always welcome to post your questions in the chat, and we will try to answer in between. So the program looks like this. It's quite a full program. And as I said, we have both hosting entities that are hosting EuroHPC Joint and taking supercomputers, but also we have users that will share their best practices with you today. And for this event, I would like to thank the hosting entities that will be presenting here at this workshop, and also the users, because without them, this event would not be possible. So, and with that, we start. So our first speaker is my colleague and head of infrastructure sector, Evangelos Floros. And Vangelis, the floor is yours.
Thank you, Lilith. Good morning, all. It's good to see so much attendance today this morning. Let me share my screen. So I have prepared an overview presentation about JU, the systems and access opportunities, focusing mainly on AI applications. So for those who are not familiar with EuroHPC, what we are an EU body and legal authority that came out from the European Commission, and we are based in Luxembourg, operating since 2018. Our mission is focusing on supercomputing. Essentially, we have assigned the role to promote supercomputing in Europe, to deploy a European HPC supercomputing ecosystem, to fund development of HPC technologies, applications, basic research, and so on. This mission has recently been expanded to include artificial intelligence, and therefore this is one of the reasons we are organizing this workshop today. So as it is mentioned here in the slide, in our recent amended regulation, our mission also now includes the development and operation of AI factories in order to support further development of highly competitive and innovative AI ecosystem in Union. The notion of AI factories essentially are AI optimized supercomputers and operate by hosting entities that, along with the supercomputers, will be offering development of skills, support for the development of know-how of AI usage in Europe, focusing mainly on SMEs and startups, but also additional AI users. The governing body of the EuroHPC is the authority that is taking decisions, the governing board. This is comprised by 35 participating countries, which are member states of the European Union, but also associated countries to European Union funding programs. And along with that, we also have 3 private partners that they are representing essentially the industry in Europe. And the European Commission is holding 50% of the voting rights of the governing boards, and providing also, along with that, 50% of the funding of the overall activities of the JU. The rest of the 50% is coming from the participating states themselves. So I will jump directly then to our infrastructure and the status of our supercomputing ecosystem today. Since 2020, we started procuring and deploying supercomputers and all across Europe. And right now the situation is, as you see here in the map, we have 8 systems which are operational and are offering resources to users in Europe. These are 5 petascale systems, small systems ranging from 5 to 10 petaflops lean back performance, and 3 pre-exascale systems, which are right now the top 10 of the most powerful supercomputers in the world. These systems are currently augmented with additional installations. We have our first exascale system currently being deployed in Germany, Jupiter. There is one more exascale system to be procured in France, for which we just opened the call for the competitive dialogue to be implemented. And also we have 2 additional mid-range systems that will be around 50 to 60 petaflops that will be either the procurement is already launched, like the one in Greece, Daedalus, or is upcoming, like the one in Sweden, Arrhenius. So this ecosystem is being expanded. We recently opened a call for the selection of the AI factories I mentioned before. And we expect the first procurements, the first systems providing AI optimized architectures to be available by the end of 2025. Switching back to our 8 operational systems, as I said, we have 3 of the most powerful systems in the world in top 10. It's Lumi. It's right now is in the number 5 in the world. Leonardo, number 7, and Mare Nostrum 5, number 8 in the world. These systems are owned by the joint undertaking. We have funded 50% for the acquisition, with the other 50% coming from the hosting entity itself. And therefore, we have the possibility to allocate resources for 50% of the overall access time to these systems. The other 5 systems, Vega, Meluxina, Carolina, Discover, and Deucalion, the JU is co-owner. We have funded 35% of acquisition cost, and therefore we also have access to 35% of the computational time, which we offer again to the European community. Overall, if we put all the numbers together, these systems provide around 900 petaflops of aggregated link pack performance across 20 partitions, 1,000 nodes of GPUs and CPUs, offering different kind of architectures like AMD Intel x86 or Fujitsu ARM, and GPU architectures NVIDIA A100, H100, and AMD MI250X. In addition, we offer a small amount of FPGAs, as well as visualization and cloud capabilities. Now, these resources are available, as I said, to European users. And who is eligible to access them? Essentially, everyone in Europe residing in an academic research institution, public or private, public sector organizations, industrial enterprises, SME startups. The only prerequisite here is to be established within the European Union or in one of the Horizon 2020 associated countries. And the access is open to all fields of science and industry. There is no specific focus on any specific scientific domain or industrial domain. We offer different ways, multiple ways to access it. I will describe the access modes in the later slides. Overall, the total resources available, which is our percentage of resources for the systems, is around 90 million node hours per year. And the exact way that these resources are distributed, the conditions and the processes are defined by the EuroHPC access policy, which has been approved by our governing board. Conditions for access. The access is for free. You don't need to pay anything. The only requirement is that you use these computing resources primarily for research and innovation, with a small exception for SMEs and startups that they can use for the results for commercial exploitation without necessity to publish the results. You need to acknowledge the use of resources when you do your work to help with dissemination events, if necessary, if invited by the JU, and also produce and submit in the end the final reports of your work in order to use it for disseminated purposes. More information are available from our website in the link I provided on the bottom. Exactly what kind of access modes we offer. So there are essentially two categories. One that's focusing on preparatory activities for benchmark and development activities, in which very quickly you can get access with small amount of resources for a period of time from 3 to 12 months in order to test your codes, to do some development activities. And then we have the production calls, which offer larger amount of resources, from regular access that offers tens of thousands of node hours to millions of thousands of node hours from the extreme scale access. This is focusing on doing research, on doing proper scientific computations, large scale on the whole systems. And these are the access is provided through a peer review process. You need to submit a proposal, which is evaluated, and within 4 to 6 months you get the results of the evaluation. Now, we recently introduced a call specifically targeting AI applications, responding essentially to requests from the AI community for faster evaluation process and shorter cutoff periods. And for this reason, we have introduced the AI and data intensive application access call. So the purpose is to offer here quickly resources. We have a peer review process that lasts only for 1 month, and we have bi-monthly cutoffs. So every 2 months, we collect all the applications that we have received, and we pass them through a peer review process. There is no ranking. We follow a first come, first serve approach. We allocate resources up to the point that we exhaust them for the specific cutoff periods. You get access to a prefixed amount of resources. There is no option to declare a preference for more or less resources, and the allocations right now are for 12 months. The process we follow is the one you see here. We accept the proposals through our web portal. All the proposals need to run through an administrative check to make sure that whoever submits the application is eligible to access based on the eligibility conditions defined by our access policy. And then there is a technical assessment by the Supercomputing Center, which has been requested to host the application, just to confirm that the application is able to run, is proper for running in the specific target system. And there is a scientific evaluation of 2 peer review experts that evaluate the excellence, innovation, and impact, and the quality and efficiency of the implementation of the proposal, and provide scoring in the end of the proposal. If the proposal is above threshold, then it is accepted for accessing the system and is awarded for access. The amount of resources that we distribute in these access calls is here in the table you see. Essentially, we offer resources from our GPU partitions, which are more applicable for the needs of the AI applications. You see that depending on the size of the system, there are smaller and bigger possibilities for allocations, and for number of applications that in every cutoff that we can offer to a specific system. Of course, our largest systems, LumiG, Leonardo, Booster, and Mars 5 Accelerate partition offer the largest part of resources and give the possibility for more applications to get access. You see the fixed allocations we have set, for example, for Lumitis 35,000 node hours, Leonardo Booster 50,000 node hours. This has been selected taking into account our experience so far regarding the level of node hours required by AI applications, but we are open for suggestions, maybe for increasing if there is feedback from the community that this amount is not sufficient and there are higher demands. And so far we had 2 cutoff dates, and we have allocated resources in 2 cutoffs, and the total amount of resources we have offered so far is 1 million node hours, more or less offering 50% of what has been available so far from this call. How you submit your proposal, you need to visit our website, our access portal, as we call it. I provide the URL here. Actually, if you try to use this right now, is not available. We are currently in a migration process from an old web address and instance of the site to a new one. The previous portal, if you have used our resource in the past, you know it was hosted by Praise, and it was offered through the Praise portal through a Praise URL. Now, Praise continues to support us in this process and offering the IT tools for the evaluations, but we're moving now to a URL and to a look and feel, let's say, that is now 100% customized for EuroHPC. So this is the address that you will use probably from tomorrow. We are trying to resolve some last-minute issues. And for any questions regarding access and our access calls, you may use the access@eurohpcg.europa.eu email. Now, having access, we understand that might be not sufficient. Some users are not experienced in using supercomputing systems, this kind of resources. For this reason, we also established an action called Epicure, which is a 4-year program funded by the JU, co-funded by the JU and participating states. The goal of this program is to establish the so-called application support teams in all the supercomputing centers offering EuroHPC systems. And these teams are here to help users in developing their codes, scaling the codes to the whole capacity of the system, doing performance analysis, benchmarking, code refactoring, and optimization in order to make the best usage of the system. Usually, there is a team allocated per proposal that work closely together with developers for a period of 2 to 3 months in order to port the code and optimize it to the target system. And the way you request this support is done when you apply for accessing EuroHPC resources. When you fill the forms describing your application, also you express your interest and requirement that you will need support from Epicure, which is taken into consideration when the application is evaluated. And once you get access to the system, then the Epicure team is informed and gets in touch with you in order to collaborate with you and support you through the process. So this is it from my side. Trying to finish quick. Don't know if
Thank
we
you
have any
very much,
questions
Vangelis.
or for later.
Questions will, I would like to ask audience to put their questions in the chat, and then Vangelis, you will be with us, I guess, to answer this. There are already questions, so I won't read it, but you feel free to answer, and then we will catch up at the end.
Okay.
Meanwhile, we're a bit over time, so I would directly invite our colleague from Lux Provide, Francesco Bongiovanni, to present the how to run workflows and AI jobs on Meluxina.
Hi. Cool. Can you see my screen?
Yeah, you need to go to presenting mode.
Okay.
Thank you. Yes, fine.
I'll just make sure it's a proper one. Yes, it's a proper one. Because yesterday I was doing a training on quantum. So, okay. So, very quickly, I'm Francesco Mangiovanni. I lead the supercomputing application group at LuxProvide. I used to manage the team managing the machine, and I was one of the designer of Meluxina. So, quick word about LuxProvide. We manage national supercomputer for the national ecosystem. We serve the research, SMEs, the greater region, and obviously the EuroHPC project as well. And we, I would say, was set up in 2020 to host and manage the machine, okay? With a strong emphasis on security. Obviously, it's important for the companies. So I will not go into detail because Evangelis just did it. So we're much involved also in the National Supercomputer, the National Competence Center, and also in the EU Master for HPC. So again, I will not go into detail about the architecture of Meluxina, but you have to just to give you a sense of idea. When we design Meluxina, we design it with AI in mind. So because we're doing AI for at least a decade before it was actually cool. So we had invested in GPU when we were in our own institution, so at University of Luxembourg and at LIST before. So I would say that's why we have so many GPUs, and that's why the main horsepower of behind Meluxina are the GPUs. Okay, but we also put I would say extra infrastructure to serve, I would say, those GPUs to the external world, and this is that's why we have also our own cloud on-premise cloud, I would say. So this is also reflected in the numbers that were given last March at the EuroHPC summit. So although we're not the biggest machine, obviously we are the biggest of the beta scale, but we are not by far the biggest. But we run a lot of first EU project and a lot of AI project. So obviously those numbers were updated because the big machines came online. But yeah, this is just to mention that we are running a lot of AI project as well on Meluxina, obviously. So we're also part of a big European project called Deploy AI, whose mission is to basically give an AI on-demand platform which adheres to the EU standards in terms of trustworthiness. So we are much involved in this project. It's a big project, 28 partners, 28 million funded by the EU. And so the kickoff was last March, so you can see that we came also to Berlin, and we're very much involved in this ongoing project. So what we did, obviously, from day one on Meluxina is to provide the software to do AI. So PyTorch was there from day one, TensorFlow, all the necessary libraries to basically run AI at scale with all the communication libraries. And for the ones that are brave enough, you can also use basically the quantum libraries such as cuQuantum, PennyLane, and so on to do machine learning, quantum machine learning. Actually, yesterday when we did the quantum training, we had many examples doing machine learning using those frameworks. It was quite nice actually. So there from day one. But you would think that is enough? Of course not, because I would say, and this is an observation, so take it with a grain of salt. The maturity of AI user is somehow heterogeneous. So we have similar questions. So they confuse a lot, I would say, parallelism and distribution. So when it comes to training at scale, so basically what they often do, unfortunately, is that they train their model in parallel. So they actually train the same model on multiple GPUs instead of doing large training on different nodes. So we have we have to assist them. We have to support them on this endeavors, I would say. So what we did for that, so we set up nice tutorials which are available on our documentation, and we've given basically three, I mean, say the usual suspect for the AI world. So we give a nice example, half an hour tutorial. You just have to follow the step on Meluxina for doing inference using specific libraries from NVIDIA, because we're NVIDIA shop. And so to host multiple LLMs, so the TensorRT and Triton framework server, AI inference server. We give also a nice example, and I will go into detail about this one because it's quite important to understand, to do distributed training. So a small example using a ResNet 50. And we also do, we give a nice example from with PyTorch to do inference on pre-trained models. So all of this was set up by my colleagues. So all the credit is theirs. So In order to do distributed training on Meluxina, you have to understand what's behind the scene in terms of communication library, because your GPU needs to communicate with one another. And there are some which I would say some libraries which are better than others. So here I would say we suggest to do communication across the GPUs to use the libnickel from NVIDIA, so the collective communication libraries, to get the best performance out of those GPUs. But you have also to understand how it works behind the scene in terms of the different layer and what's basically happening in between the layers. So in your convolution network, basically. So this is a ResNet model with 50-layer model, okay, with all the stages. You don't need to understand that. But what we give is first a helper function in Python, and then we give the model and also basically the script. And the script basically follows this kind of, I would say, workflow. You have to give obviously all the stuff directive, and you have also to load proper software. You need also to set up all the distribution, so the architecture, because when you do data parallel with PyTorch, you have to set up, you have to do some plumbing before you start basically your training, and you have to do that correctly. And we give you some nice commands to do that. Okay. So then you have also, and this is quite important, to enable the optimization, the communication library, especially with NIPCL. And what we have also seen is we have two network cards per GPU, but most of the users are only using one. So we give also some tips to how to use the two, basically to take advantage of the big bandwidth that two 400 gigabit per second card give you. So this is quite important as well. This has a big influence on the training. And then after you run it, and you have to provide all those parameters to basically have the best performance. So we give that in our documentation. Those nice examples work at scale, but still, some people still have issues. So this is a small example of the ResNet. So this is the main function. Again, those are the steps that you need to do basically to set up properly the DDP. So you first have to set it up. So we have nice functions which are very nicely done to set up first the architecture behind the scene. Then after you load your data, you load it with specific byte size. What we have seen also is that users tend to I would say, are very cautious regarding the batch size. They come with really small batch size, and they could go higher. So again, those are knobs that you have to tune, and you have to find, depending on the size of the data set, you have to find yours, obviously. You have to prepare the data loader with respect to the batch size, obviously. And then after, you have to instantiate the trainer with the optimizer that you will need during the training. What we also provide, and this is quite nice, is an example of how to use snapshot feature of PyTorch, because when you train large model, chances are that at some point one node will crash on you. So it's good to do snapshotting during the training phase. So we give you also some helper function to do that, an example to do snapshotting during the training. So if something fails, basically you don't have to start from scratch. And then you basically launch your training at scale. Okay, so those are the steps that you need to do to do that. You would be surprised by how much performance the user leave on the table. So just a quick example. We did the maintenance a couple of months ago, and then day after the maintenance, one of the users was basically reporting a slowdown in his pipeline. I was like, okay, so we checked, and actually there was a new parameter in Slurm, and that was not as the one before. And so we fixed it. So he went back to normal, performance. But then after I start to have a look around, and this was particular because it was doing training on CPU. Say, fine, okay, some people are doing that. It's quite interesting. But just by changing one line of code and making sure that I was basically taking advantage of the NUMA domain, making sure that all the streams were done set up properly and according to the number of NUMA domain of the CPUs, and also changing just one line of code and changing the way to run the application, so making sure to pin I would say the thread to the physical cores and so on, I was able to get an 8x performance improvement just by changing that. So you would be surprised how much they leave on the table. So that's why we also support them at that level, especially so to do proper profiling of the application. I will not go into detail, but that's the things that we also do. So there are some AI-oriented profilers which are quite nice. So one is Kalin, it comes from the University of Massachusetts. and the other one from NVIDIA called Deep Learning Profiler. So we give some example how to set it up, what it gives you also in terms of feedback, how much time you're losing in the Python interpreter, in the native part of the interpreter, how much data you're copying back and forth, and so on and so forth. And this will basically give you a sense of how much data movement you are actually doing, and if they are necessary or unnecessary, because sometimes they are unnecessary. So we give this, and this we do generally in the context of the Epicure project. So then we can zoom out, and also the NVIDIA Deep Learning Profiler is also nice. It basically allows you to go even deeper and give you some suggestion on how to basically improve your training at scale and so on. So this is a more contrived example, but works great on Meluxina. So this is the kind of, I would say, UI that it gives you in terms of tooling. It's quite nice, I would say, to go deeper in terms of performance. So just I will go quick. So what we also do, and this is also in the context of Epicure, and we did it actually for the e-translation team at the European Commission. So what we did is we try to do the optimization across the whole pipeline of the deep learning workload. So how to avoid a lot of small files. So we give example of how to use HDF5 format to basically put all your small images, because Lustre doesn't like small files. So we give some example, we help them how to also use the local disks which are on the GPU nodes, because we put those especially for that actually, and how to use also the scratch here to get even more performance. Regarding the DI, I would say the training phase, it depends obviously on the kind of model, but let's suppose that you're using the transformer model, then we also give you some hints and guidance regarding the attention layer, for instance. You can use Flash Attention V2 or V3, which was recently released. And also framework which help you basically optimize across the whole transformer model. So DSML from ETH, Zurich, the Thunder, DeepSpeed from Microsoft, and Colossal AI, which basically can also optimize your workload. Same for inference. There are many opportunities in terms of optimization, and we're also very much testing basically AI inference on FPGA. So that is ongoing work. So quite nice. Get even more performance efficiency. So just to finish, we're also testing inference on CPU. You'll be surprised how much you can get out of those CPUs. There was a nice project from Mozilla Research called Llama-File, which basically was also pushed by a great engineer called Justin Tenney. And she basically set up a discussion how to basically benchmark basically Llama-File on CPU. And yours truly also submitted our numbers regarding basically a Mistral 7B on CPU, and we get basically great performance as well in the 200 tokens per second. So on CPU, I mean, a human can only read at 5 tokens per second max. So we have 250, so more than enough. So we are investing in, I would say, a lot of some efforts around this. So, and also on FPGA. And last example, so we are also doing, because we have an on-cloud, an on-premise cloud using OpenStack, we deploy some services, long-running ones, such as Langflow, to do even more user-friendly pipeline. And we have did the integration between the cloud and the rest of the machine. So what we did, we run basically Langflow on the cloud, and then after it's easy as 1, 2, 3, literally. So you run Llama on one of the nodes, okay? Then after you run your model, so here it was a Llama 2 70B, and then basically what you do, so in a small example, and we finish with this, is basically you do this Langflow and you ask question to your own LLMs that you're deploying on Meluxina. So here, I'm sorry for the flickering because it's a GIF, but I have asked, what do you know about EuroHPC? And basically you will get the answer and so on. That is, and quite actually get it right in terms of answering. So it doesn't hallucinate much, I would say. But this you can play with many LLMs. You can create your whole workflow and test basically multiple LLMs in parallel and so on. So this is good. It's quite nice. So this we're experimenting. We're not offering that to the user yet because it doesn't sit, I would say, behind a 2FA. But users basically can instantiate their own, I would say, VM on our own OpenStack, and we'll be able to actually do that. So this it's also in the setup. So yeah, that's about it. Thanks.
Thank you very much, Francesco, for a really great presentation and all the tips and tricks you showed. And now I would like to invite Mohammed Adel, who is the user of LuxProvide Meluxina, to actually show how he applied all this on a practice. So Mohammed, the floor is yours. We see your slides now on the presenting mode. And if you unmute, then yes.
Can you see?
Yes. So
okay.
Welcome.
Hello, everyone. Thank you for a great presentation previously. I hope our work of Meluxina actually not the one sending these messages. So I will present our work in user best practices and result on Meluxina for overall our team. Starting by introduction of our research group and work here in CVI2 University of Luxembourg. Some short overview of Meluxina. I think it was well covered in previously. And our system architect access, how we work with Meluxina, some case study and the result we obtain for our research, and some tips for maximizing the performance and some pitfalls to avoid. And finally, conclusions. So we are a computer vision, imaging, and machine intelligence group, University of Luxembourg. Our main focus on computer vision, image processing, image analysis, machine learning, with 22 members, 10 PhD, 15 master students, and we receive about 13 million funding since we started, with a lot of collaboration between industries, public institute here in Europe and internationally and in Luxembourg. So our work is spanning from developing AI application for space, trying to give some kind of special intelligence to a spacecraft to have space situational awareness, detecting object in space, catching debris. We have also worked in 3D scanning and reverse engineering from a 3D scan to a CAD files, which request huge amount of processing, especially for 3D models. We have also worked in detecting deepfake and mitigation and trying to prevent like deepfakes in images or detecting if any temporal modeling happen to the image. So giving all our research with mainly images and videos and 3D models and quite heavy stuff, we need a lot of GPUs. And we are very happy that we have Meluxina. So Meluxina from LuxProvide here in Luxembourg is 18 beta flops compute. I think it will cover in the previous presentation. And so just to go fast in this part, we have the login node, the compute node, some storages for like, where you are either putting your data files or training or different parts. As a general kind of like overview, starting from the login node to the compute node, like different directory for different objective, from like personal space to having the files, the project part, which is temporary, no backup. If you have important data, we need to move. So overall, like just to show the idea of having different storages and every part to have a specific application. And we use mostly Slurm for the resource management part, from like checking the job, submitting it, all the following all the job steps, and here like some and kind of like general overview of the execution and workflow, from creating this batch script, submitting the job, viewing the job, monitoring, and execution. An important thing is always check GPU utilization, make sure kind of like taking all the possible GPUs, making sure like you are well utilizing the available GPU, and also like optimizing based on that your data loader to have the maximum GPU usage. Then the part about like is environment and working with the model system, like batching, like containing everything from Bison virtual environment, making it like, making sure CUDA version, PyTorch version, TensorFlow version. So for experiment or for predictability. Here is just a short example of using the SPatch script for job submission, and also like having a separate folder to store essential batch script for different project and configuration is quite important to make sure that you have, and again, can reproduce the same results, specific if you have publication, if you have an experiment, having reproducing the same general behavior is very important. Also for the data management and synchronization between like your local configuration and working in Melixina, using all like, mostly we also use like VS Code and resync extension configuration between local, like your computer VS Code and on the server. And also for configuration for the remote Melixina. Another important part about like optimizing technique for loading data is making sure that like your pre-processing and data pipeline is where is actually the most used part is. For example, using multi-thread and multi-processing, especially given that we work mostly with images that will have a lot of data augmentation, pre-processing, all the steps, having like where exactly this happened, how it's happened, what is the number of like images that will have, some pre-processing or data augmentation technique. Some of them work in CPUs, some of them work in GPUs. So making sure like which part having in what processing is very important, especially for images or 3D data, which most of the time come as graphs and nodes. So also optimizing the batch size, not just for the compute part, but also for the data augmentation part and the data pre-processing before passing it to the model is very, very important. Making also for the using the GPU memory training in mixed precision and is quite useful for training bigger size model and saving the checkpoint, of course, but not all of them, like just to make sure you don't actually over save what you need. Here is also like a nice tool from I think PyTorch, where you can do like a memory snapshot and see what like how the memory iteration happen over iteration and between the forward and the backward pass. Another part is using parallel training. Mostly like we using like distributed data parallel from PyTorch for using a multi-GPU setup and fine-tuning based on that the batch size and learning layer and communicate the overhead for distributed training. Another part is also monitoring your usage, as we mentioned before, making sure utilizing all the possible GPUs and all is the best way to go. So using something like MyQuota to check the storage quota, monitoring the utilization of the GPU in real time. You can also like use your own logging system, Whistler. So again, the part about saving checkpoint, because there is tendency to save everything, which can be quite big, especially with if you are using like something like transformer models or what's called now foundation models. Checkpoint became quite huge as a size, and if you save in every iteration, this will be like quite an overhead from data size quite fast. Another part, which is more advanced technique, is something like using Singularity container for creating consistent environment across different systems. So having like using also this, so instead of like using like building the Docker images for across all the platforms, so you can reproduce and re-implement the reproduce this experiment again. Also having parallel experiment launches, so running multiple experiments simultaneously. And this is important as more complex and efficient use of Moluccina, so you can have more like training with fully containerized image. Just to give of what we actually used Moluccina with in our research here, Project Da Vinci, where we used deep learning for like from 3D scan to generate reverse engineering and create like regenerating the 3D CAD model that this 3D scan was based on. And we used different like GPUs for like distributed parallel training in this case, with increased batch size, learning rate, and for that like reduced training time from 2 to a half hour to 30 minutes. Another part is using also training for efficient pose estimation using knowledge distillation. And here we used 50 GPU for memory, and the objective was kind of like training larger model with high number of parameters, high energy consumption, but the objective is that this model need to be deployed on edge device in space. So the need for like optimizing this like model parameter using knowledge distillation is very important. But initially we need to have a bigger model size, and for that we used Moluccina for the training. So using like a higher bigger GPUs with bigger batch size. Another case is deepfake detection. Now with the problem with easy access to deepfake, there is a lot of work trying to detect if any image was manipulated. And the idea that our main research is using this deepfake detection techniques. And for that, we have this model transformer based learning framework. And this idea that we use the Moluccina also 40 GPU, 40 GB GPU memory node with parallel training, and this was high throughput, speed up compared to other uses and other HPCs. Just another example also for Earth observation data. And we have a project also with LuxProvide with Moluccina AI for CC for Earth observation. And especially for Earth observation, there is like millions of images and like, huge amount of data coming from space every hour actually. And here we did like implementing parallel training for pre-training a transformer model. As was mentioned before, for the data set we use HDF5 files. So we have also the data passing to the GPU in bigger chunk than just images. So, but also handling large number of input with multispectral data. So there is not just RGB image, there is multiple image. We also use vision transformer, which is much bigger model size, and especially in training in self-supervision, the need of much bigger compute and much bigger like passing data batch is very important. And with Moluccina, we managed to actually achieve this. Here, like for example, our model is about 100 million parameter, very computationally expensive, and also the input giving that it's multispectral. So also the input image is also huge in size. And we managed to run this in Moluccina quite easily. So just some point, always use all GPUs on single node for efficient GPUs node consumption. Adjusting the learning rate with scaling the batch size, and scale the batch size to fit the GPU. Optimize the code for training process for better GPU utilization, as we see the profiling part. So this can be used for seeing what part can be passed to GPU and what part consuming a lot of a lot of GPUs or CPUs. Using singularity container for consistent environment is also quite useful. Implementing efficient data pipeline, as I mentioned, working especially with images, there is a lot of data augmentation and pre-processing. This is quite important. Using multi-thread and the multi-processing for data loading is useful, especially if you are working also with images or graphs. Fine-tuning and communicated, all of that can be tested and like kind of run a small experiment before you started the distributed training, so they can just test the kind of smaller batch size. Some pitfalls to avoid is not checking all GPU utilization, saving all checkpoint instead of essential one. Basically, you will find that your directory started to overflow with checkpoint is that very not really important. Most of actually the bottleneck come in the data loaders, not the training as a model. By the time the model started training, it's much easier, but your data loader, data processing is mostly your bottleneck. Logging also important, and profiling your code to make sure where is your bottlenecks. Underutilizing available GPUs in Node will get you to in problems that you can avoid and you can improve and fasten your training. So just in conclusion, Molexina offers significant performance for us. We are very happy with running experiment in different direction and different research topics. We have a proper resource allocation optimization, and it's very crucial for maximizing efficiency. Monitoring and adjusting your parameter and seeing how actually the training happened during the training or before profiling is very important to lead to optimal performance. Having something like singularity containers and the parallel job can be useful, but it's more advanced. So if you are happy with the basic use case, no need to go this direction. But if you have more complicated setups, singularity container can help. And always check your GPU utilization. Further resources, documentation is very well written and quite with nice examples that you can copy and replicate with your experiment. Just learn documentation, singularity, and tutorials. Thanks for also the team who provides their use cases and how they use Molexina. Thank you very much.
Thank you very much, Mohammed. It was very interesting, especially to see the advice you provide using all the GPUs on a node, for example. I see a hand for a question, but unfortunately you cannot ask the question, but you can type it in the chat. And I already see questions to you, Mohammed, so I would like to ask you to answer. Yeah. A reminder to all that please post your questions in the chat and we will address them. And now let's fly from Luxembourg to Finland. And our next system is Lumi, and I would like to invite Mats Sjöberg to share how to use Lumi in a most efficient way for AI.
Hello, can you hear me and see my slides?
Yes, we see well and we hear you well. Welcome.
Good. Okay, yes, so my name is Mats Sjöberg and I work as a machine learning specialist at CSC, which is the National Supercomputing Center in Finland. And I will talk about Lumi, which is the HPE Cray EX supercomputer, which is actually the fastest supercomputer in Europe, and it's on spot number 5 in the whole world. And as has been mentioned before, it's of course owned by EuroHPC JU and hosted by this Lumi consortium. You can see the countries there in the map. Physically it's located here in Finland, in Kajaani. You can see the dot there, more or less in the middle of Finland. And kind of the hosting side of things is done by CSC, the National Supercomputing Center here. So I will not go into that many details, but I have this slide about the specs of Lumi. So there is a CPU partition, you can see there, and then a GPU partition, which is kind of the at least from my point of view, working in machine learning is the most important or most interesting part of Lumi, and which provides the biggest chunk of the kind of computing that it has. A special thing about the GPU side is that we are using AMD GPUs, MI250X GPUs, and these GPUs are actually a bit special. They have 2 compute dies. So even though we have 4 of those AMD MI250Xs, they are each consist of kind of 2 GPUs for all intents and purposes. So you can count with 8 GPUs, or more correctly, GCD compute dies per node. So if you count all the nodes and all the GPUs, we have almost 24,000 GPUs in the whole of Lumi. And then, of course, a fast interconnect between the computers and what you would expect normally to have. I also mentioned here the Lumi-O, which is a kind of object storage system, which is similar to, for example, if you are familiar with Amazon S3, this can be also used in Lumi. So I was supposed to talk more about how to use it, so kind of workflows and those things for AI. So there are 2 ways to access Lumi. The traditional one with terminal access with SSH connection, and then there is also nowadays a web user interface, which is becoming more and more popular, and this is based on logging in with your web browser, and you can see there a screenshot how it looks like when you log in. Of course, you can also here start a terminal and use the familiar terminal commands, but there are also various other applications you can start up from there. So here I have a slide showing some of them. So you can run Jupyter notebooks, for example, when you are developing your code or running simple experiments. Then down to the right, I have an example of running TensorBoard. This particular example actually is showing the PyTorch profiler, so it's a nice way to do profiling of your code. In this particular example, I'm debugging a problem where it seems that the GPU is not utilized that much. You can see there what is marked with 1, it's doing some heavy processing in the CPU, and these are the situations where you then get low utilization, and you need to check for better solutions. Which we don't have yet on Lumi, we have on our national systems is MLflow. It's coming to Lumi also, I believe, and it's shown there in the bottom left. So another way of tracking experiments, and especially for machine learning. So you can plot your different experiments and take a look, for example, how some, let's say, accuracy or some other parameters are improving, hopefully, during the training. So for the software environment, as the previous speaker also mentioned, Singularity containers are quite good, and in Lumi we recommend them for machine learning applications. And so Singularity is quite similar to Docker, but it's better suited for these multi-user systems that are the supercomputers. And we also provide some tools for users to easily make their own containers, for example, this container tool mentioned here. Of course, we also provide pre-installed containers, so not everyone has to build their own. So we have containers for popular frameworks like PyTorch, TensorFlow, and JAX. And I would also like to mention, you can see at the bottom of this slide, there is a link to machine learning guide, where we have tutorials how to run things on both a Finnish national supercomputer and also in Lumi. For example, how to run on multiple GPUs with this PyTorch distributed data parallel was also discussed in the previous talk. And especially for Lumi, when you are going even larger scale, then you might need other more advanced frameworks like fully sharded data parallel or deep speed. And we have some tutorials how to use them. So this fully sharded data parallel is, for example, useful when you are training large language models where maybe your entire model is so large that it doesn't fit into one GPU memory. And we also have in that machine learning guide some other tutorials, for example, how to do fine-tuning of large language models with various frameworks like the Accelerate framework. So one big thing about Lumi, or let's say big distinguishing factor, is that Lumi uses the AMD GPUs. So I'm often asked about that. Is that a problem? And the answer would be mostly no. So PyTorch, which is the clearly most popular framework among those that we support, so it's pretty well supported out of the box. And also lots of these recent additions that are used, mentioned here below, like flash attention, VLLM, and so on. They are being ported by AMD to work on AMD GPUs. So I would say that for most projects you won't notice any difference, especially if you are using our pre-packaged containers, because we have all these additional bits and pieces, we have compiled them for you for AMD. But for like large scale jobs, and if you are doing really bleeding edge research, there will be still some rough edges, because NVIDIA is usually the first platform where the support is added, and AMD comes afterwards. And I believe the next speaker after me will represent one of these very large scale cases. So Sampo can tell about that the next talk. So for data storage, we have the traditional parallel file system. We could mention here particular there is a flash storage as well, which has much higher throughput, which can be quite useful for some cases. And then this object storage that I mentioned already can be nice in many cases, especially users coming from cloud background and are used to that kind of way of working. And as with the previous system with Meluxina, Lumi also uses Slurm for scheduling jobs. I will not then spend so much time on that. But you can see here the normal GPU partitions that are available. Here is a slide showing a scaling experiment made by a colleague of mine, where he is doing basically training of a large language model, and he was able to scale up even to 3,000 GPUs on Lumi. And you can see here the plot to the left, which is called strong scaling. So here we are indeed keeping the batch size constant and scaling up. So you can see that like linear projection would mean that if you have one GPU and then if you go to 1,000, it would be exactly 1,000 times faster. That's basically not achievable. Basically because how this basically how this training task has to be distributed, and there are parts that have to wait for other parts to finish before they can go on. So that's not even theoretically possible to have exactly linear scaling. And then the weak scaling, where you get more close to linear, that's where you increase the batch size as you go to more GPUs. So that's kind of easier case to do. So finally, some words about workflows in general. So our main users, of course, on Lumi are academic researchers, and that's why kind of our way of looking at things is always with flexibility in mind, because academics, they want to pick and choose what tools to use rather than us telling them, okay, this is how AI workflow are supposed to work, but they want to pick something from here, and they have their own custom solution from there, and so on. So that's why our approach is to support many tools. I mentioned already some, like the TensorBoard and MLflow, but there is not kind of predefined integrated workflow as such, but we provide support for users, so they often approach us that, okay, I want to do this kind of thing, what are the appropriate tools to use for that, that we help them with that. So to make things more concrete, I have here an example workflow that is quite common. So user would prepare a container for the software that they need. Quite often they can use the pre-made ones or modify them. And then you can use this Lumio, for example, to store your datasets, your training datasets, maybe your completed models. And then for checkpointing, recommend use the Scratch file system. So it's always a good idea to make checkpoints during your runs. In case something crashes or something, you can always go back to the latest checkpoint. Or then if you have really long runs and you are running against the maximum runtime in Lumi, then you can continue again from the previous checkpoint. And then using Slurm, you can of course submit multiple jobs. These can be parameterized, so you can submit, for example, 10 jobs or 100 jobs with different hyperparameters. And then you can use something like MLflow for tracking these runs. Okay, this last slide just has some useful links to the main documentation of Lumi and the machine learning guide I talked about before. All right, there is a nice picture of Lumi in Kajaani. It's situated in old paper mill, so you can see that in the picture. All right, thanks for my side.
Thank you very much, Mats, for this nice presentation. And now that we know how to use Lumi, I would like to invite Sampo Pissalo from University of Turku to share his experience of using Lumi. So,
thank you, and thank you for this opportunity to present our work on Lumi. I'm sorry, I need to rejoin in order to share, apparently. Just a moment.
Okay, but in that case, let's do a bit of a change in the program and then invite Laura Morselli to describe the system we have in Cineca, Leonardo. Laura, you're here?
Yes, I'm here. Can you hear me?
Yes, and we can see you. Maybe you can jump in to until...
No problem. Just let me know if you can see my screen correctly.
Yes, we see your screen. So we now describe Leonardo, and then we go back to the test cases and usage on both systems.
Okay, perfect. Then, well, good morning, everybody. I'm Laura Morselli. I work at the supercomputing department of Cineca, and I'm here to present Leonardo and how this infrastructure is optimized for artificial intelligence workloads. So just really 2 words on Cineca. Cineca is a consortium made of more than 100 members. There is the Ministry of University and Research, the Ministry of Education, all the Italian public universities, as well as other research centers and public organizations like hospitals. And we are located in 5 different cities, more or less spread all over Italy, and we are currently more than 1,000 employees. But for what concerns the supercomputing department, we are around 110, 120 employees. So currently, Cineca hosts the Leonardo supercomputer, which, as we heard this morning, is the 7th most powerful supercomputer in the world, according to the top 500. And I want to spend just a few words on its architecture. So it has a booster module that has almost 3,500 nodes. Each of these nodes is equipped with 4 NVIDIA 800 GPUs with 64 GB of RAMs and one single CPU Intel Ice Lake with 32 cores. And then we have a general purpose data-centric partition with almost 1,500 nodes, and each of these nodes is equipped with 2 CPU Intel Sapphire Rapids with more than 50 cores each. So you can see the peak performances of the 2 partitions. We have 200 petaflops for the booster module and 9 petaflops for the data-centric general purpose module. We also have an interconnect, a low latency interconnect and an Ethernet interconnect, and a storage that is more than 100 petabytes. We have a capacity storage and a fast tier storage. The fast tier is based on DDN exascaler full flash. So this is what we have right now available for the users in Italy and in Europe, but there is also upcoming an upgrade of Leonardo, which is the Lisa partition, which is represented in the left side of this picture. And Lisa is really an AI optimized module with that will have more than 160 servers, 8-way GPU servers, and also a low latency interconnect, which is currently one of the best in the market. And we will provide in kind also storage data lake tier of 25 petabytes. So this is the facility that will be available to the users most likely at the second half of next year in 2025. So now that we have an idea of the resources available, I will just want to spend a few words on how you can access these resources. So Leonardo is co-funded 50% by the EuroHPC joint undertaking and 50% by the Ministry of University and Research in Italy. For what concerns the Italian part of the resources, you can access them via ISCRA calls. ISCRA stands for the Italian Supercomputing Resources Allocation Organization. And there are different types of projects. So we have the Class B that allows for a maximum request of 250,000 GPU hours on Leonardo Booster with an allocation period of 12 months. And Class C, which are smaller projects, a maximum of 10,000 GPU hours on Leonardo Booster for an allocation period of 9 months. To access these calls, the PI needs to be affiliated to an Italian research institution, while no restriction is applied on the co-PIs and collaborators of the project. And on this type of projects that are allocated, that are awarded the compute resources, Cineca provides high-level technical support through its user support group. For what concerns the European part of the resources, we have already heard this morning from Vangelis the type of calls that are available, but I just wanted to write down the quantities of hours for what concerns Leonardo, because you can access different quantities of resources based on for the different supercomputers. So for the benchmark access on Leonardo, you can ask for the booster. I'm of course focusing on the booster partition because for the AI workloads is the one that is most requested. You can ask to up to 3,500 node hours. So you have to multiply by 4 if you want the GPU hours. For the development access, 4,500 node hours. And for the regular access, you can see the window that goes from 52,000 to 220,500 node hours. For the AI and data intensive application is 50,000 node hours, and for the extreme scale, you reach a minimum of 245,000 node hours, so more than 1 million GPU hours on the Leonardo Booster for 1 year. So this is how you can access the resources. And of course, we also, for the Italian part, we have a pay-per-use utilization of the cluster. Now I want to spend some time to describe the Cineca artificial intelligence ecosystem. So Cineca started a few years ago what we call internally the Cineca AI project. So on the Cineca infrastructure, on the supercomputer Leonardo, there are some softwares that are, let's say, available to the users, and they are accessible via modules. So they are pre-installed softwares available for the users. So we decided to create modules that are called the Cineca AI modules that collect all the most used libraries for AI workloads and different, let's say, versions, because we know that when the users come, they already have their scripts that are prepared with a specific version of a library. Sometimes it's not straightforward to move from one version to the other. So we have currently different versions of Cineca AI, and to these different versions correspond different versions of the libraries inside. We keep these modules always up to date. So as you can see, in the past 1 year and a half, I think, or maximum 2, we went from Cineca AI 2.0 to Cineca AI 4.3. And you can see inside really the most used libraries from the users. Of course, you don't have to, it's not mandatory to use these libraries. You can come with your, you can recreate your own environment on our machines, but the pro of using this environment is that they're really optimized for the type of GPUs that Leonardo has. So they're optimized for the underlying architecture, and they're prepared by the Cineca experts. What you can also do is to create your PyEnv, so your virtual environment, pulling packages, pulling libraries from the Cineca AI environments. So this is for what concerns the virtual environments that you can find already prepared. Of course, another very a problem, let's say a challenge, is moving hundreds of terabytes of data, and this is becoming more and more clear also to us as a hosting entity. So now currently we have data movers nodes. So we have dedicated nodes on each of our clusters that are designed to for transferring data from and to the clusters. And these nodes have some protocols that are available, for example, rsync, SCP, SFTP, vget, and curl. What is the advantage of these data movers? That there is no, let's say, wall time for the users to use these nodes, because on the login nodes of Leonardo, as I will say in the next slide, there is a wall time of 10 minutes. So everything that you try to run on the login node is killed after 10 minutes if you don't, for example, use a job script, as we will see later. Our ecosystem includes also our own experience on the infrastructure. We are learning that we have to keep up to date constantly because things are moving extremely fast, and we are trying to do so. So, for example, we recently finished an internal project of running MLPerf on our cluster, for example, running the training of GPT-3 and running the fine-tuning of Stable Diffusion. And this gave us a lot of experience on how to optimize the use of resources on Leonardo. Here, instead, on the left, you see scalability, an exercise that we did on the scalability of the training of Stable Diffusion. So these are all, let's say, experience that we are building up internally to stay up to date and to offer support to our users. In progress, we have some works on making available to the users workflow and data management libraries, for example, MLflow and Pachyderm. And also we have available several courses on the Cineca AI Academy. These courses, the material of the courses is available for everyone. It's publicly available. You just need to click on login as guest, and you will see courses on deep learning, on also in introductory courses on large language models, on efficient use of resources, basic courses on Python, Julia, R. Of course, here I'm focusing more on the artificial intelligence part, but then there are also all the other courses related to more traditional workflows. There are hands-on, there are the slides, and for some of the courses, there are also the recordings. So it's material that you can really exploit to prepare your to interface with the Leonardo cluster. So how the user interacts with the supercomputer. So the supercomputer is the part here inside this orange rectangle. So of course you SSH into the login nodes that, as I said before, have a wall time of 10 minutes. And so to access the compute nodes that per se have no access to the internet, to the outside internet, you need to write a job script. A job script that looks like the one, the screenshot here. So it's a file where at the beginning you write dispatch directives that are the requests that you do to the scheduler in terms of resources that you need. So number of GPUs, for how long, how much memory, if you want an exclusive use of the node, and so on and so on, what partition you want to run. This job script is submitted to the scheduler via a command, which is dispatch. And then the scheduler allows you to go on the compute nodes on the partition that you have requested. So here you can see an example of job script, and I'm sure that the speaker of the use case on Leonardo will also talk about porting and changing, let's say, the mindset on interacting with the supercomputer. Once you have granted some time on Leonardo, you and your project is active on our supercomputer, you have access to different data areas in Leonardo that are accessible via environment variable that you can see written here. And they are associated with different quotas and also with different attributes. So some of the areas are specific to the user, so only the user can access it, and some others are project specific, so all the users associated to the project can access that area. For example, now we have a fast scratch, well, let's say a fast data area that allows for faster input-output operations. The normal quota is 1 terabyte, as it is for the work area. And this would be a good place, for example, to write your checkpoints, or also on the scratch. But writing on the scratch, depending on the size of the data itself, can be slower. So usually there is a benchmarking phase where you decide in which area you want to write your checkpoints, for example. And there are commands, very easy commands to monitor your occupancy that are chin data and chin quota. Now, as I said before, things are moving extremely fast, so we need a continuous improvement to allow us to provide meaningful support to our users. And here I try to write down some of the challenges that we have faced in the recent months and the solutions that we have provided to the users. So, for example, some of the users were facing slow input-output performance on the HDD storage, and so we provided access to an improved input-output full-flash storage, which is the fast scratch. Of course, the AI jobs with long runs and higher number of nodes may experience system instability. It's just more likely, when you ask for thousands of GPUs, that you might experience system instability. So we have to share best practices on checkpoints. And again, the user of Leonardo will talk more about how they decided, how they found the sweet spot for writing checkpoints during their training. And so we do also a lot of interaction with the users to help them and support them on finding this sweet spot. In general, we try to explain to the users the pros of using the Cinecare environment, and also we are trying to improve the usability to keep the modules always up to date and promote also the awareness of the HPC services to the AI communities. In general, of course, the user, when it comes to our infrastructure, would like to have reserved resources and not to end up in a queue, but this is not possible in our infrastructure. And so we need to improve also the skill of the AI community on an efficient and sustainable use of the AI system, and also to make them aware of what it means to have reserved resources if they're not used, consumed properly, because they would just be wasted potentially. So we are doing a lot of training also to increase the exposure of the AI community on HPC system, of what it means to port environments and to port workloads, so on and so forth. In general, and I finish with this slide, this is the support that we give to AI users. There is a layer of general HPC related support services, which is true for all the communities that approach our infrastructure. And then we have a series of dedicated services tailored for the scientific and industrial artificial intelligence community. For example, we support on estimating the needed resources, both compute and storage. And this is needed when you interface, for example, the EuroHPC calls to access. Now you need to give an idea of the resources that you're going to use. So we support you on doing that. We support the porting of the application on the HPC infrastructure, the use and mastering of the AI libraries on HPC architecture, the upscaling of workflows, the engineering of data pipelines to be more efficient. We give support on the pre-training of large-scale AI models, so to scale up to really thousands of GPUs, but also for the fine-tuning of these models. So we have internal competencies on everything that is associated with fine-tuning, and also to set up retrieval augmented generation-based workflows. And right now, for example, recently we also created, let's say, the internal competencies in order to provide support for the exploitation of large language models for creation of synthetic data. So, for example, this is possible with Llama 3.1. We have the 405 billion parameter model, which is great to create instruction-based data set that will be used, for example, for the fine-tuning. We are involved on several projects that provide support. So we think that also we can provide efficient integration with the existing and upcoming support-based European initiatives like Epicure that was mentioned this morning. But I just want to mention also the upcoming Minerva project, which is the European AI Support Center. So that should support all the artificial intelligence users in Europe. So with this, I thank you very much, and I will take your questions on the chat.
Thank you very much, Laura. Really very nice presentation, and it's nice to see the definition of different levels of supports and project. I see already 2 questions in the chat, so I would like to ask you to answer. And meanwhile, we are a bit behind the schedule, so let's have a break now for 10 minutes and get together 11:15. And then the second half of the workshop will be on use cases to continue with Lumi, Leonardo, Mainostrom, Vega Carolina. So 10 minutes break, and then we all start at 11:15. Thank you. So then we start. I hope everyone is back, and I hope our speaker, Sampo Pissalo, you're here.
I do. So let's see if I can share my screen now. So I hope this is.
Yeah, we see your screen, but not the first slide. Sampo. Is it me or Paolo? Do you hear me?
Yeah.
I think we lost Sampo, so I think you start. I think Sampo has technical problems. So I would like to invite you, Paolo Albano from iGenius, to share your experience on Leonardo in Cineca.
Give me a second that I try to share just the tab.
Let's see if it works.
Do you see my screen?
Yeah, we see it. Thank you.
Okay. Hi to everyone. Good morning. I'm Paolo Albano. I'm an engineering manager at iGenius. And my primary focus, my job is I'm focused on work on natural language processing and all our conversational aspect of our product. What is iGenius? Simply, iGenius is a company that is focused on try to reduce the gap between the people and the data through using the AI. Our goal is to enable everyone to explore the company data and ask business questions in just directly natural language. And we are committed to making data accessible to everyone in a secure and private way. And we try to support the businesses in highly regulated sectors. So this is our motto. We help company transform data into decision intelligence. Here are some of our customers, Italian, European customer. Our main product is Crystal. And Crystal is our AI-powered decision intelligence tools for analyzing your business data of a company in a natural language. And we are trying to make Crystal to make data analysis feel like if you are talking with your colleague. What we are developed with Cineca on Leonardo is our first lateral language model that is 100% open source, is a 90 billion parameters with a context size of 4,096 token. We developed our tokenizer with a vocabulary of 50,000 tokens. We train everything from scratch on trillion of tokens. The idea is to create Italia, this model to capture linguist and cultural nuances that you can't have if you train your model on English dataset, on translated dataset. Everything is on MIT license. Why we are using Leonardo to develop everything? You need to start to understand that there is a model complexity. So there are complexity on different aspects. We can start thinking about the memory consumption, because it's okay. You have a 90 billion parameters models. Each param is floating point, 32-bit floating point, so 4 bytes for parameters. And you can simply just do the calculation and you will get 36 gigabytes. Then you need to think that, okay, you need more memory also for optimizer. So you need around 3 times the parameters, because you need the same amount of memory to store the gradients, the first and second moments. We are using Adam. Need also to understand that you need to store also the batch memory. So that is based on the batch size on match token for each batch, the context length, and also there are also other overhead memory that you need to store that are related to network communication. If you are doing the granted accumulation, some PyTorch buffer. So we can say that we are around 4 times the memory that you need to store all the parameters of the model. Also, there is also complexity related to dataset. We released our first, in June, we released the first version of our model where the dataset we created from scratch dataset that is composed by mostly Italian data. Dataset size is around 1.2 trillion tokens, and on disk it takes around 4 terabytes of data. And we are still working on it. We are increasing the dataset, changing composition for the continuous pre-training, and now we are reaching the 3 trillions of tokens. So the data are also increasing. So is not only related to memory, but also where to store this data and access fast this data. Previously, when we are moving to Leonardo, we work simply on Cloud Vendor. When we need to start a multi-node job, we simply use torch run, essentially starting one or more machine, so different nodes, and starting manually with the torch run the job. And okay, you can speed up this phasing using Docker or some Ansible script, but when you are trying to move everything to Slarm, we found that it's very easy because you can simply bring everything that you have directly on Slarm cluster, write a single batch file, and launch the job. So, and also move everything. If you are using PyTorch, as in our case, is very straightforward. So you don't need to create or change your code to do everything, but just write a simple batch file and launch it, and everything is working. And also this helps you to increase your training job, adding more nodes, and it also very easy, but just changing just one line as batch file. Okay, we are trying to find to write a comparison between use Leonardo or just use a cloud vendor. We understand that, okay, big pro is to have a dedicated resource. When you use a cloud vendor machine, you are not sure that you are using dedicated resource. Your node, you are pretty sure that is shared between multiple users, multiple jobs. So if you get exclusive access to node, you will find that you increase your performance. Also, if the hardware is the same. Is you can get also in great control over the environment, because okay, as Laura say, you can directly load a module with everything pre-configured, but it's also easy to create your software stack, add your customized code with hardware optimization. Scaling job is very facilitated. So just also in the early stage of project, when you start your job with 3-4 nodes, just to understand that everything is working, to run some debugging, and then changing just one line, you can relaunch everything because we have pushed our job to 300 nodes, very easy. The porting of everything is, if you are using PyTorch, as in our case PyTorch, or other framework like Lightning, the porting of the training is very simplified. Is maybe just one day you have everything that is working. And also another important point is the GPU provisioning. The provisioning of nodes with GPU on a cloud vendor is not always very easy, and maybe you need to wait sometimes because there are sometimes regional limitation on some cloud vendor, or maybe you need to contact the sales agent of a cloud vendor to enable you to access more node and have more GPU. But with Leonardo in HPC, it's just simple to submit your code where you have also just fast feedback that to give you when your job will start. So I think it's this speed up also your experiment. Cons, you should think that okay, there is a small onboarding phase. So we spend, for example, a week to understand how to use cluster effectively, how to work job submission, queue management, the dependencies, how to make the monitoring, and other things that not all clusters are already LLM ready, because okay, we are talking about memory, we're talking about dataset, but it's not just related to use a modern GPU that support, for example, flash attention, but also is something related to communication between nodes, for example, InfiniBand or high-speed storage. So, and also you need to think that a normal job of training of a large language model take several days, lot of days. So this introduces some complexity. What I have understood that, okay, you need to start thinking about the GPU load optimization. Okay, you should try to achieve a GPU utilization between 70 and 90%, making a lot of tests to identify what are the best hyperparameters. Under this threshold, okay, the nodes is underused. So, but if you go up, you will find other problems that can slow down your training process. So if you reach 100% of utilization GPU, sometimes we get your training slower because, okay, one more GPU maybe can increase the latency. So some GPU can create just a bottleneck for all training. You are triggering very often the PyTorch garbage collector, and these can increase the time for each training step, and also you can incur the risk of out of memory. So you need to find for starting of a project, find what are the best parameters related to kind of nodes, and also are very related also to structure of your model. So a monitor tool is essential for this evaluation. Okay, we use a weight and biases. We find that the problem that okay, the nodes of Leonardo are not directly connected to connected to internet, and the standard usage of weight devices, and during training it sends information to 1DB platform. You can find a lot of workaround on this. For example, you can set 1DB mode to offline and then sync manually every day, couple times for day, and sync everything, and you have essentially the same dashboard with all information. Also, for everything you need to download from internet, the idea is always pre-download everything, store in a cache folder. Also, for example, if you think about dataset from Hugging Face. Another optimization you can do is related to checkpoint strategy, because you will spend time to save and load checkpoint from disk. So during our test, we see that in each phase, and for resuming from a checkpoint, it takes around 1 hour, and moving, for example, to using high performance file system, that is the fast partition of Leonardo, we see that there is a decrease of this init time from 1 hour to 20 minutes. Another good strategy could be you save each the checkpoint around 3-4 times the duration in each phase, or just equivalent number of steps. Also think that the checkpoint for a large language model, as we say, as you will store all the information about weights, optimizer. So this takes a lot of disk space. So the idea is try to reduce the number of checkpoints kept. Maybe save all the checkpoint based on metric. For example, just put the val loss value in the checkpoint name and then clean your data. You can also think about try to optimize the checkpoint using a distributed checkpointing. For example, if you're using the DeepSpeed as framework, this provides some tools for manage distributed checkpoint. And also another thing that, okay, a job can fail, or maybe one node fail, simply create a strategy that automatically resume the process from your latest checkpoint. And using directly, what we're doing is just directly using the dependency between jobs. This can automatically restarting from last checkpoint without any manual intervention. Another optimization that we have performed is the pre-tokenization. Okay, why pre-tokenize? Simply this speed up training, because tokenization is a CPU intensive job. So if you pre-tokenize everything, this increase your training time, so you can store directly the tokenized version of your data. This reduces latency because the nodes don't need to tokenize the data during the training process. You can simplify your code because you don't need to think about tokenization during training. So it's just think about read and how to manage this data set. You can also think, if you tokenize, if you perform the pre-tokenization, you can create a dedicated job for this task to avoid to use GPU nodes, so you don't waste resources and you don't block other processes that can use the GPU. And also, you will know the exact number of tokens only when you tokenize your data. So this enable you to also create different partition of your data set, and also this make you to make some decision on data management. So because during the training you will have different phases, and you also to try to, okay, we will try to find the best approach how to mix your data to increase the performance of your LLM. Okay, other resource optimization is related to training parallelism. If you are using PyTorch, DeepSpeed, you will know that you can make data parallelism and model parallelism. Data parallelism, okay, is very easy to implement. Each GPU take a portion of data, and this can be used on relatively small model. So maybe around 3-4 billion parameters. When you increase with the size, okay, you need to move to model parallelism. So split the model across multiple devices. In our case, we found that seemed that best solution was use FSDP hybrid. That is a strategy that apply full shard of the model within a node. And this way, you optimize the training because okay, all the parameters are replicated within a node, so this reduces communication. That also could be a bottleneck, could be a problem that during the training essentially. Another optimization, okay, we are talking about floating point and store 32-bit for each parameters, but during the training, you can also move to use a mixed precision training. So use both BF16 when you are on NVIDIA GPU and 32-bit floating point 32. So this speed up your training to make faster computation, also reduce memory usage and overhead during the communication between GPU. Also think always to gradient accumulation. That okay, this enable a large training with okay, you can increase the batch size without exceeding memory limits. This improve also the training stability. Think also always during the hyperparameter search. You will find this, and if you use this with a correct weight decay use, and also think always about learning rate, this can improve the performance of your model, speed up the training, and you can ensure that your training will finish without the risk of memory overflow. And that's all. Thank you to everyone.
Thank you very much, Paolo. This was very useful to see. And with that, we try the next with Sampo again, but this time we will try to share Sampo your slides, and you are welcome to direct us.
I could also try to share my whole screen if that might make a difference. I'm not sure if the window versus anything
Okay,
else
try again, and then Elise will share
if
your
it crashes, let's go with the backup.
Yeah, and Paolo, I would like to ask you to keep an eye on the chat for the questions.
Okay.
Thank you. And so Sampo will present the best practices on Lumi. We see your screen. Yes,
And
I think you can
maximize it.
Yeah, or otherwise you can go this way as well.
Okay. Excellent. So it seems that I might actually get to present these after all. So thanks again for the offer to present some of our work. And apologies once more for the technical hiccup. Seems Teams was not on my side today. So just to briefly introduce myself and our group. So I'm a research fellow at the University of Turku in Finland. My background is in computer science and machine learning. And my original field was natural language processing, although now mostly I think we would all like to call it artificial intelligence. Our group is a couple of decades old. We're about 30 members now. And of those 30, we have about 10 people working on large language models specifically. And the work that I'm going to be talking about is mostly in the context of the High Performance Language Technologies project, which is a Horizon Europe project now in its second to last year. And the project is seeking to introduce text resources as well as language models and machine translation models for a large number of languages with an emphasis on European languages. And in our group, we've been focusing on large language model pre-training from scratch. And before I go into the results or what we've been doing, I do want to acknowledge that we also collaborate fairly widely within Finland with National Library, and we've also had the privilege of working with Hugging Face, AMD, as well as the Finnish startup Silo AI, which was recently acquired by AMD. And all of our work has been supported by CSC and, of course, Lumi. And we've been working on Lumi since the earliest availability of the system in late 22 with a pilot project on the Lumi. And we've created a number of large language models, actually a number of large language model families. Over the couple of years of this work, we've been awarded allocations totaling in excess of 15 million GPU hours, which is a fairly sizable amount of compute, much of this coming from the Finnish national allocation, which is the biggest slice of which is the biggest national slice on Lumi. During the pilot, we created the first very large Finnish language model called FinGPT. We trained from scratch to 13 billion parameters and 300 billion tokens, which seemed like a fairly large model and large amount of training data at the time. But of course, things have changed somewhat since then. Also during the project, the pilot, we created a model we call Bloomy by continued pre-training of the largest Bloom model. So that's 176 billion parameters. We continued pre-training it for about 40 billion tokens. So those were our initial efforts to introduce models emphasizing Finnish capabilities in particular. Those were then followed up by the Poro model, which is a Finnish model, Finnish, English, and code capable model trained for 1 trillion tokens. It's a single model of 34 billion parameters. And we're currently finalizing the release of the Viking family of models, which span from 7 to 33 billion parameters and are trained for 2 trillion tokens of all the Nordic languages, English as well as code. We're also currently working on models that cover all EU languages as well as code, and those will probably be ready sometime in 25, although the specific plans there are currently in flux. And I'd like to briefly talk about some of our results. So the results for the monolingual Finnish models, or the models that emphasize Finnish, are probably not terribly interesting to anyone outside of Finland, but we were happy to note that already in our earliest experiments, we were able to substantially improve over previously available models for the Finnish language, although with some indications of overfitting for the largest models. We were then able to, in creating the Poro models, which are bilingual plus code, we showed that through the addition of data in languages other than Finnish, we are also able to improve on the Finnish capabilities of these models. And we were very happy to note that the 34 billion parameter Poro model outperformed the Bloomy model with more than 100 billion parameters. So by investing more into pre-training, we're able to get a better model that's more efficient at inference time on top of that. We also reached broadly competitive results with open models that are trained for a similar amount of parameters and are similar in terms of their parameters and pre-training token counts for the English and code. In addition to the somewhat pragmatic goals of creating these models that enable AI applications for Finnish, I'm happy to say we've also had the opportunity to contribute to some more basic research. So Lumi was used in a collaboration led by Hugging Face that established the first data constraint scaling laws, which is a very interesting question for anyone working on languages that have limited training data. So perhaps the highlight takeaway of this is that doing 4 epochs over your training data can be done without compromising the performance of your model as compared to having completely new data throughout. So I wanted to share a couple of perspectives about what we have been able to achieve on Lumi. So from the very earliest, we had access to fairly substantial amounts of compute on the European scale. And so we went with quite ambitious model sizes and continued to try to push this in terms of how many tokens we train on and how large the models we train are. And here you can see our models in blue and Llama models, which are considered fairly state-of-the-art open weights models, although not fully open models. And up until earlier this year, it seemed that we were lagging somewhat behind, but still playing the same ball game in terms of training, for example, the Viking models on an equal number of tokens as Llama 2. However, this did change earlier this year with the release of Llama 3, shown here quite substantially dwarfing our efforts, both in terms of how many tokens it's been trained on, a very impressive 15 trillion, as well as the size of the largest model, more than 400 billion parameters. So this is kind of game over for us as in terms of trying to make an open frontier model, that is, in terms of trying to create an open weights model that would have capabilities that are not found in other open weights models. Of course, we can still compete in terms of being more open, being more replicable, being more transparent about how these models are created, which is something where Meta doesn't always shine. So a back of the envelope calculation, just to illustrate how far the distance is between what resources are available to us and what is available to the tech giants, is if we were to try to replicate the Llama 3 training process on Lumi, we would require approximately 100 million GPU hours, or roughly speaking, the whole system for a whole year. A couple of words about the practicalities and experiences. So mostly, in order to do LLM training at the largest scales, you'll want to use dedicated frameworks for this purpose. And a lot of the advances there are focused on NVIDIA GPUs. Lumi, of course, as Mats alluded to, being an AMD system. And a lot of those advances are implemented in specialized CUDA kernels, with the AMD versions sometimes being appearing quite a bit later and not always functioning great out of the box. So we've done a bunch of porting and debugging to make this possible in the first place, and still frequently being approximately a year behind the state of the art in terms of, for example, having access to flash attention. We've also, due in part to these reasons, seen some limitations in terms of what sort of throughput we can reach. So in Poro training, we got about 100 teraflops per device. So for both of the GCDs of an MI250X put together, meaning that during this process, we were getting about 70 to 80% out of an MI250X, what we would have been able to get out of an A100. We have gotten some better throughput in recent experiments. In terms of the software, we initially worked with Megatron DeepSpeed, kind of cross-porting the ROCm ports of the fused kernels of this framework. This, as all of our work, is fully open, although I have to say that specific framework I would now consider completely deprecated. And more recently, we've been working on the base Megatron language model, or a fork of that, that allows us to also use flash attention too. And in both of these frameworks, as alluded to in several previous talks, it's important that we're able to rely on custom containers that have been created by CSC, as well as earlier through our collaboration with AMD. I would also like to recommend, there's a lot of movement recently on AMD side, kind of increasingly recognizing the importance of LLM applications, as well as the capability to train the largest of language models on their platforms. So there's now several frameworks that explicitly support AMD, including Ulether's GPT-NeoX, Hugging Face's Nanotron, as well as there is an AMD port of the transformer engine created by NVIDIA originally that supports their most recent Megatron language model framework. I'm also putting here some instructions in case someone is interested in testing these on Lumi. So these are instructions, forks with instructions created by a member of our group. Finally, I'd like to say a couple of words, share a bit of perspective about the prospect of creating frontier models on Lumi as well as other EuroHPC systems. So because on these systems you have to compete in the queue with other users of the system, and there are some issues with hardware failures, node failures, and a number of other factors that can cause delays. In practice, the time that the calendar time that it takes from starting your very large training run to its completion can be substantially larger than the time that it would take to do continuous compute to get that model done. For example, in Poro, we took more than 4 times the idealized compute time in order to get the model done in practice. And losing half a year to being on the queue or being held up by a service break or other issues is a long time in LLM development and can really make the difference between having a state-of-the-art model and one that's kind of middle of the pack. Finally, just to briefly share my current perspective of where Lumi is suitable, and I think this does apply to other EuroHPC systems also. So for pre-training from scratch, if you're working under 10 billion parameters, everything should be fine. If you're trying to create a model from scratch, trained computationally optimally to 100 billion parameters, you're probably not going to make it. Even if you get the compute, by the time your model is done, it's already too late. The field has moved on. So between this 10 billion to 100 billion parameter range is, I think, a slot where we can still negotiate the possible. However, for continued pre-training, as well as, of course, fine-tuning and inference, Lumi is an excellent platform, and I think this is where we should increasingly be focusing our efforts. I will, with that, since I am already running slightly over time, I will leave you with this slide with my thanks and acknowledgements, and I will be very happy to answer any questions you may have on the chat. Thank you.
Thank you very much, Sampo, and thank you for great slides. It's interesting to see your personal view, considering that we are about to procure AI factories. So again, reminder to all, you can pose your questions in the chat and our speakers will try to answer them. And we move on to the next speaker, and next speaker will present his experience on the Vega supercomputer, which is in Slovenia. So I would like to invite Iztok Lebar-Bajic from University of Ljubljana, Slovenia. Iztok, you are with us?
Yes, just a second. I'm starting to share my slides. Okay.
Okay, thank you.
So yeah, I can let me reshare.
It's fine. We can see it.
Yeah. Wrong deck. That's the problem.
Oh.
Anyway, yeah. I come from the University of Ljubljana, the Faculty of Computer and Information Science, and I've been a happy user of Vega since its early days. At least as part of my group and colleagues, we've been mostly using it in machine learning and AI. In other words, we do not care much about the CPU partitions. All we want are GPUs, the more the better. Now, our primary focus is on conversational AI, meaning that on development of models that are an essential part in natural user interfaces, such as speech recognition, natural language processing, and speech synthesis. Here, we primarily focus on the Slovene language. Why the Slovene language? Because it has quite a small speaker base, and most Slovenes understand and speak at least one foreign language. So most commonly, that one is English. This makes Slovene language rather uninteresting for the big companies. And since the speaker base is small, data is also scarce, or their acquisition basically very challenging, to say the least. And as you all know, at least in machine learning and AI, data is one of the most important bits there are. In the last couple of years, we've been involved in several projects that are trying to remedy this situation. Most of these had multiple institutions co-involved, but for the sake of brevity, I'll skip the listings. They can be found on their respective websites. Now, the first one that I'll mention is development of Slovenian in a digital environment. Its primary focus was to prepare corpora and develop models and tools to be licensed under permissive licenses unavailable through public repositories, free to be used by private and public entities. Its biggest result was the Arthur dataset. It is a 1,000-hour transcribed speech dataset to be used for speech recognition systems. There were also a lot of demos, tools, and models that are all shared to the public and all available through the website Slovenština EU. A side project of this project was the benchmarking toolkit or portal specifically dedicated to the Slovene language for various language technologies tasks. The other project that was basically a co-side project started for the university, and it's called Online Notes. It is supposed to be a automated transcription and translation, live transcription and translation of university lectures aimed at students, Erasmus students that come to visit Slovenia and don't understand Slovenian, as lectures are mandatorily given in Slovene language, as well as students with disabilities, for example, hard of hearing, or to be used as a learning aid by the students, by the other active students. It's been an active development for the last couple of years, and we're just preparing to go on a larger production level deployment throughout the university. And the last but not least is adaptive neural net, a language processing with large language models, POVEIMO for short, which is dedicated to devising a Slovene large language model specifically dedicated to the Slovene language. And our first results will be upcoming, come out in the upcoming weeks. I've been invited here today to talk just a little bit of our practices that helped us to keep our sanity during the earlier mentioned projects. It has been mentioned quite many times that data is basically the most important portion, but will not go into this bit, even though it represents a lot of challenges, and many times the reasons that data owners, for example, many of whom are public institutions, are reluctant to share or even sell their data to be made publicly available, is out of fear that the AI will make their jobs basically useless, which is a very hard premise to fight against. In recent years, there's been a general trend to portray ML and AI research as factories. In this sense, there's a box, you put data in, you shake it, wait for a while, and out comes a model. As simple as that. Anyone can do it. Many tools try very hard to keep the appearance that there are just a couple of knobs, and that most of the time the defaults are automatically perfect for any case and scenario. We've seen today that this is usually not the case, and we face quite a lot of challenges when doing so. The development process, otherwise, is traditionally termed basically somehow MLOps, or machine learning operations, and most traditionally portrayed as a multi-stage pipeline. Here with 3 stages: data preparation, training and customization, training and deployment, of which only mostly training and customization happens on HPCs. Data preparation is more of the sense in the early stages of acquisition, curation, and so forth. And artifact archival and use traditionally is more deployment and inferencing, again, not strictly on the HPC systems. On the HPC systems it's the training and customization that happens. Here, the MLOps traditionally concentrates on 2 phases, on the experimental management and iterative training. And this is what we also did during our processes. In our case, we chose the NVIDIA NeMo toolkit. It is an open source toolkit developed by NVIDIA that started up by covering the conversational AI pipeline, ASR, NLP, and TTS, but more recently expanded to LLMs, MMs, as well as computer vision. It has been in active development since 2018 and currently reports approximately 11,000 GitHub stars. The name stands for neural modules, expressing the concept of modularity that was adhered to during development. It is based on Hydra for simple configuration management via YAML files, with the included possibility to customize the individual run also via parameters passed during the execution calls. NeMo leverages Lightning and PyTorch to provide for easy scalability to thousands of GPUs, hardware-dependent precisions like BrainFloat 16, Floating Point 8, or the upcoming FP4. It supports all sorts of advanced parallelisms that become essential once the models start to grow beyond the boundaries of a single GPU. And on lower levels, it is based on Nickel for efficient inter-GPU communication. We chose to do pure container-based training, as many of other colleagues mentioned. That is a very good and very traditional way of going in machine learning and AI. For the management, we do not install NeMo on bare metal via models. That's what the containers are for. Because there are simply too many dependencies and there are high chances of things going wrong, like the introduction of undesired or non-noticed differences in setups that are caused simply by the absence of dependency pinning. NeMo is unfortunately notorious for this portion. NeMo Python requirements list alone has approximately 130 libraries. Sadly, a large portion of them is unpinned. Containers then are a perfect fit for this purpose. They allow for the creation of an immutable tooling that can be used anywhere. NeMo containers are regularly built by NVIDIA and freely available on NGC. Furthermore, we manage and version our code with Git, data with its data versioning companion DVC. For experiment tracking, visualizing and live monitoring, we use weights and biases. And for artifact storage, we set up our own MinIO S3 repositories. Throughout the years, our SBatch script submission scripts have evolved and grown, the key motivator being standardization, naming schemes, trackability, and repeatability. What you see here is a short snippet of our SBatch scripts that mostly follow the same modular design, with a portion dedicated to setting internal variables, followed by a portion dedicated to the execution scripts, here highlighted in blue. And finally, the actual Slurm core, which loads the correct container image, meaning tooling, mounts the data and experiments folders, and calls the earlier prepared execution script. This execution script is prepared dynamically. In this specific case, we take advantage of Slurm's capability to start up the required number of tasks, knowing that Lightning will infer the correct distributed processing parameters out of Slurm's environment variables. In essence, this means that if the underlying code is capable, one can go from single node, single GPU training to multi-node, multi-GPU training by chaining just 2 parameters in the script's header. That is the number of nodes and number of GPUs per node. All of the execution scripts that are prepared dynamically follow the same pattern. They set up some additional environment variables. On this screen, some of them are commented out as they become important only when doing low-level debugging. The earlier mentioned environment snapshot debug code, or PM, is inserted here as well. It is used, it is basically very verbose dump of the current environment on software system, on hardware systems, on compute systems. More on that later. A 1DB API token is used to connect to the weights and biases portal. And finally, the actual Python code, with the config that is specific to the experiment is called. Here it provides a gigantic list of additional parameters passed via the call. The script is again dynamically generated, and the SBatch script is written in such a manner that it will copy itself as well as the dynamically generated script into the locked folder that can be passed via a parameter version into the SBatch, so that we have a track record of every experiment that is run. This allows for later on repeating the experiments or keeping track of all the changes that are happening during the calls. Working within a very active domain presents its own set of challenges. Toolkits can appear and disappear quite rapidly. New models arrive daily. And with the advent of LLMs, this is getting only exponentiated. More and more data scientists are entering the arena. This means that to stay at the top of the game, even the more seasoned toolkits need to adapt, and sometimes this may introduce breaking changes. Such an example was PyTorch 2.0, and which its set of changes that introduced, but it did also introduce Torch Run, which may potentially help making SBatch scripts simpler. A similar thing is going on with Nemo 2. Currently, it's still under development, which is introducing a more Pythonic and flexible startup procedure that will eventually probably replace all SBatch scripts and will just call Python-like code. That being said, to be lucky when choosing your toolkits is for sure one line you should strive to have on your best practices list. What follows is a short list of some of the challenges that we faced during our use of Nemo on Vega. Some were more stressful than others. But mind though that they are not toolkit or cluster specific. Running jobs on a single GPU is nowadays basically smooth sailing. With the advent or with the use of VS Code tunnels, we found even multi-GPU single task development and debugging sessions quite a pleasurable user experience. You simply start up a VS Code on a compute node, enter it, use the tunnel to enter the node. Since you loaded the precise or the desired container, you basically feel like using your own virtual machine somewhere in the cloud. Things start to get a little bit more fun in quotes, beyond the single task job.
Sorry to interrupt. Yeah. We have 1 minute left.
Okay, I'll shorten up and speed through these things. Basically, avoid using GPUs per task because it will drop the okay. I'll skip this one. Just okay. Try not to assume that the order of the task startup will be always the same. Slumber start the jobs in a non-deterministic manner, which may cause you later on problems because the logging will be out of order, or trying to load an unfinished checkpoint will again lead to crashes and so forth. Random crashes may be caused due to flaky nodes. Flaky nodes are nodes that are in Slurm environment marked as idle, but not drained, even though their state is invalid. The state can become invalid because of sysadmins that are doing rolling deployments of GPU drivers, packages, or OS updates. And the only chance you have is to do debugging, meaning finding out the correct environment state on the system and then excluding those systems out. And library dependencies, interdependencies can be a really, really big pain. For example, we had such an experience with the interplay of OMP threads, OpenMP threads, and Number, where Number is in this, as soon as you check the number of threads the Number is using, it resets the number of OpenMP threads used by the system, which can lead to over provisioning the entire system and meaning slowdown. We notice it by having a slowdown of 4x on our trainings. So all in all, to shorten everything up, if I return to the start, what I would want you to leave out as best practices, know as much as you can about your toolkits, know as much as you can about your hardware, and be kind to sysadmins and maintainers because they're your friends.
Thank you very much, and thank you for your tips. Interesting to know about library interdependencies. And we go forward with the next speaker as time is pressing, and I would like to ask you to keep an eye on the chat for the questions. And I would like to invite Kathy Sitia, a user of Carolina system from IT for Innovation. So, yeah, we can see your slides. Okay, the floor is yours.
Thank you. My name is Kathy. I'm a researcher in IT for Innovation National Supercomputing Center. Okay, it's not going to slide. So some of the AI projects that we work on includes like mostly segmentation of medical data images. So the first project you see is segmentation of liver, tumor, and veins. Another one you see is multi-organ segmentation. This project is, the next one is object detection. One is analysis of slurry coatings. And others like anomaly detection and combination of holographic and safety protection. So these are some of the computer vision projects that we work on. So this is a image of how the Carolina infrastructure is. It has both accelerated nodes and non-accelerated nodes. The accelerated nodes has 2 processors and 8 GPUs with 40 GB per GPU node per GPU. Here you can see how you can get access to Carolina cluster. So if you would like to access, you can go to you can create an account, IT for an account, and get an SSH key and get a project. Or for any difficulties, you can contact the support. Here are some ways of transferring the data to Carolina cluster. For example, for serial transfer, there are SCP, SSFS, and SFTP. And for parallel transfer, you can use rsync hyperq. For very large files, you can use HQ transfer. For Linux users, they can use Midnight Commander for transferring files within the terminal. And for Windows users, you can use PuTTY or WinSCP. Allocating cluster resources for on Carolina also there is a Slum scheduler. So using SBatch, you can take CPU or GPU, or you can take interactive job using Celllock, and you can view the workload on Carolina by going to the dashboard. Here you can see how you can load modules. There are already existing modules, so you can load, unload them. For example, you can load TensorFlow, which is existing, or you can, in the next slides, I will show you how to create your own environment. So these are some of the ways of creating your own environment: Conda environment, virtual environment, Apptainer, and directly installing it. For example, Conda environment, where you have some complex projects and you need non-Python dependencies, and virtual environment when you want to have simpler projects and you can use Python's built-in tools, and Apptainer to directly create portable and move across different workstations. So here I show you how you can create virtual environments. So this is the first one, is the requirements file. Using that, you can create the virtual environment and then submit the job by SBatch. Similarly, this is for PyTorch. Similarly, this is for TensorFlow. Then I show the Conda environment, how you can create Conda environment on Carolina. So either you can simply create, pull from the Docker Hub, the Docker, the Singularity image, or you can create your own YAML file and create your Conda environment. This is for PyTorch, and similarly, you can create for TensorFlow. Another way is creating containers. You can build your own container, or you can pull some container which is already available. And then you can mount a hosting directory. So see, these are some of the examples how you can host. And then here I show 2 examples how you can load PyTorch and TensorFlow containers. There are more ways, but we will stick to this for now. Here I prepared example project, which is focused on the segmentation of liver tumors. So this is the workflow: data processing, model training, inference, and post-processing. And we try both on single GPU and multiple GPU. So this is the result on Carolina. You can see the inference, and the time taken on single GPU was 5 hours 40 minutes for a validation score of 85%. And with if I take 2 nodes, 16 GPUs, so it was done within 50 minutes and reached similar score of 84%. And this is, you can find the code here, and you can submit the script by this slurm batch script by activating upon the environment. So you can try out this example. So we try to parallel process the training of the neural network model. So here we set up the environment variables, the rank of the rank and the world size. That means how you can assign the rank to each GPU and determine the world size so that every GPU has a specific task for parallelly processing and running the epochs parallelly. This is achieved by DDP by PyTorch. And this is how it's done. You can use a distributed sampler data loader to distribute the data among different GPUs you have allocated in your job. And then you have to move your model to the device. And then using DDP, you can wrap your model so that the gradients from all the GPU flow and it's collected by one single process. So we finish until all the processes are completed, and then we save the model. Then learning rate is adjusted also by the number of GPUs. Here we save the model only by process 1, and TensorBoard logging is also done by process 0. TensorFlow, you can view the TensorBoard with port forwarding. Here is an example of how you can do port forwarding and view the TensorBoard locally on your browser. This is example with TensorFlow. So when you train on multiple GPU, you can watch how it's progressing. You can check the GPU memory and the percentage. So here you can use the command watch NVIDIA SMI. For CPU memory, you can use the command htop. Checkpointing. So this is very good practice to do checkpointing because the jobs has a limit number of hours. For example, on Carolina, it can be 48 plus, almost 48 hours. After that, you need to run another job and use the same checkpoint. So it's good practice to do checkpointing. So here an example with TensorFlow and with PyTorch. So if the training stops, you can resume the training by using the checkpoint you already saved in your first job. This is job dependency using Slurm. So if your first job, if you want to run your second job directly after your first job, if it's dependent on the first job, then you can do job dependency, especially for this checkpoint purpose. So once your first job is completed, you can use the saved checkpoint in your next job. So it will start right after the first job is completed. This is distributed hyperparameter tuning. So for getting the best hyperparameters, you can do a search using the ray trace library. So this example is for that. So here you can see how you can use RayTune distributed trainable creator, and it will search for the range it has been provided. OpenMP can be used for parallel inference. because it's not inherently suited for multi-GPU training because it has a shared memory. So this example is to do parallel inference using OpenMP. If you would like to do parallel inference, you can use a concurrent library from Python, a Python library. And for example, by using this, the time on my project was reduced from 30 minutes to 10 minutes using 4 processes. So not even just parallel inference, you can parallelize your for loops or any other code using this concurrent library. MPI can be used for similar to PyTorch. MPI also can be used for parallel training, distribute your workload on different GPU. So there is a library already available, MPI for PY. You can directly load it on Carolina and use it to parallelize your epochs and data distribution. Another is model parallelism. If your models are too large, like large language models, LLMs, so you can try model parallelism where you distribute your model into several paths, into several layers, and run each on different GPUs. Here are some tips for dealing with large data sets. So some of them are use chunked data loading. Instead of loading all the data set at once, load in chunks. Use data to directly GPU. Use data generators. Clean up your memory after it's used, after every epoch. Then you can use distributed sampler for distributing your data to different GPUs. Similarly, you can do data sharding, where you split the data set into smaller shards, allowing each process or GPU to load only its assigned shard. So these are some of the practices when dealing with large data sets. And then there is infrastructure monitoring. Here are some commands which you can use for monitoring your jobs and checking your resources and information about your partitions. So that's all. Thank you.
Thank you very much. And thank you for the presentation. And again, everyone is welcome to post their questions in the chat. And with this, we move to Spain, to our last but not the least pre-exascale system, MyNostrum 5. And I would like to invite Monica Damier, who is the CEO of Nextmol, to present her experiences on MyNostrum 5.
Can you see my screen?
Yes, we see it. Thank you.
So good afternoon, everyone. My name is Monica Damier. I am the CEO of Nextmol. So my presentation is going to be much more application focused than the previous one. So we are a spin-off company of the Barcelona Supercomputing Center. We are devoted to computational chemistry, and we mainly develop a software as a service platform to accelerate the R&D of specialty chemicals based on molecular modeling and artificial intelligence. So our mission is to help the chemical industry in its green and digital transition. And when we talk about specialty chemicals, we mainly focus on polymers and surfactants. In terms of molecular modeling, we use mainly molecular dynamics with the code GROMACS. For AI, we use machine learning techniques mainly based on scikit-learn. And we are ISO 27001 certified on information security, which is very important for our customers. Here you can see some of the use cases that we calculate very often for our customers. So, for example, we can calculate a migration of additives in polymeric matrices, and here we calculate diffusion property. Additives for improved performance of detergents. Here we calculate critical micelle concentration, surface tension, interfacial tension. Also, we have worked a lot on agglomeration inhibitors, and here we calculate absorption energy, agglomeration barrier. Also, cooling resins is a remarkable use case where we calculate thermal conductivity, or also encapsulation of active ingredients, where we mainly focus on solubility. And also, very often our customers require that we design new polymers which are bio-based to replace traditional fuel-based ingredients. And here, well, we calculate many different descriptors, but some of them are glass transition temperature and mechanical properties. So we have extensively access to supercomputing resources through PRAISE before, and now through EuroHPC joint undertaking. So we had run our calculations in Juvels, in Meluxina, and now in Mare Nostrum 5, always for open R&D purposes. And well, these calls, well, they are open to all fields of science, industry, and public sector. And here I want to remark industry access. So there is a special track for industry where the principal investigator needs to come from industry. So this is, yeah, what the track we use every time that we participate. And here I'm going to show you the results that we have, the results of the latest project that we have run under EuroHPC, which have been published in a publication that you can find here on the right-hand side. So, and the title is Predicting Glass Transition Temperature of Biopolymers via High-Throughput Molecular Dynamics and Machine Learning. So here what we have done is we have started from a large list of monomers, which are, some of them were bio-based, others not. We use unsupervised machine learning methods to select the most relevant candidates, so to select, to do some prioritization instead of starting from thousands of possibilities. We do some clustering and decide just to run a few samples. Then we run high-throughput molecular dynamic simulations where we calculate glass transition temperature. And with all the results that we obtain with this data set, then we train machine learning methods, so supervised machine learning, so that we can screen a very large amount of polymers in a very short time frame. So here a little bit more details on how we do it. Here. So we combine machine learning and high-throughput molecular dynamics to efficiently sample and characterize the chemical space. We have developed simulation protocols that are reliable to calculate glass transition temperature. For at the beginning, we started with 58 homopolymers. Okay, we calculated these homopolymers. They were in very good agreement with experimental reference data. So we use the same simulation protocol for 488 copolymers, where we did not have experimental references. So in total, we ran 2,184 simulations because we did 4 replicas per polymer. So we ran a total simulation time of 143 microseconds. And with all these results, as I said before, we train a machine learning model for the prediction of this calculated with molecular dynamics glass transition temperature with a mean absolute error of 19 kelvins and a score of an error score of 8.83. So you can find all the details in the paper. And you can also access for free this machine learning model in this link. So as I said before, in total, we computed 546 polymers in a high throughput, so completely automatized way, where we filled each simulation box with 10 polymer chains of around 2,000 atoms each box. So we created all these polymers with our own polymer builder that is able to construct homopolymers and copolymers, block and random of any size, which are very well pre-calibrated compared with the state of the art. So we chose the system so that we had a density of around 0.5 grams per cubic centimeter. And here we use, for this high throughput, mainly the GAF force field, but for some particular bio-based polymers, polysaccharides, we had to use GliCam6 to be able to obtain good results. So you can find all the details of the calculations. Here, the main conclusions is that, we have chosen GROMACS because it runs very well on GPUs. So we launch calculations to be very well benchmarked and very well optimized for running on GPUs. So we have experience with A100 in previous systems, and now with H100 of NVIDIA, and we are obtaining very, very good results. And just to finish my presentation, which is mainly focused or addressed to industry. So EuroHPC calls are a great opportunity for industry, but also SMEs like us to access supercomputing resources. The purposes need always to be open R&D that you will publish later. Codes need to be ready for HPC, which is not always the case, but if you have such a code, let's use this opportunity. Also, we are very grateful to help the support, which is excellent, has been excellent through all the 3 different supercomputing centers that we have access, and they have helped us a lot to tune our scripts and to run in the best possible way in all the machines. And also, we find that in many machines, you need to have a very good planning of the calculations because you have a time-distributed allocation, so that you cannot wait or launch all your calculations at the end of the grant period. So thank you very much. It has been brief, but I hope that it has been interesting. Thank you.
Very interesting. Thank you, Monica, and thank you for the nice words to our hosting entities. And I see again hands, but please type your questions in the chat, so we'll answer this in the chat. Thank you very much, Monica. And then I would like to invite our last speaker again about Mainostrom 5, Aitor Gonzalez Aguirre. Aitor? Aitor is from BSc Spain.
Hi.
Let's try.
Can you see my screen?
We see, but not on a presenter mode, I think. It's still okay. You can proceed this way. It's fine.
No,
we can see them.
Yeah.
We could see them well, anyways, but.
Sorry about this. Can you see it now? Better?
Give 1 second. Yes, it's perfect. Thank you.
Okay, sorry about that. So my name is Aitor González Aguirre. Let me check something. Okay. So I am from the language technology unit from the BSc. I am the team leader of the language modeling team inside the unit. And I'm going to present the work done by our team
with the Mare Nostrum 5. Okay, so I'm going to start with some context because, as you know, language models such as OpenAI's GPT, Google's Gemini are trained primarily in English, and this limits their performance in other languages. And so, we have to overcome this limitation. We have three national projects called AINA from the Generalitat of Catalonia, and Ilenia and Modelers from the Ministry of Spain to develop models and resources for English, for other languages than English. So we collected a huge corpus of 10 trillion tokens for 35 European languages plus code. And the Mare Nostrum 5 is new, we had the opportunity to use the full supercomputer during the pre-production period. So we trained these language models for 1 month before it went into production. Okay, so first of all, I'm going to present the Mare Nostrum 5. Can you see my pointer?
I'm not sure, but we see your mouse.
Yeah, okay. So here in the middle, you can see the hard drives. This in the right part, we have the accelerated partition. This is the general purpose partition and the communication. And these are the long-term storage, the tapes, magnetic tapes. Okay, so we have like 25 racks for storage with a total of 200,000 terabytes. We have 90 racks for the general purpose partition and 34 racks, totaling 4,480 H100 GPUs, okay, with 64 gigabytes each. So I'm going to skip some of the slides because some of the topics has already been covered. So I wanted to speak about 3D parallelism, but as you know, you can to train large model, you need to split the model into the different GPUs and different nodes. But the typical bottlenecks you find when doing this, and you try to scale it to a large supercomputer, is this are summarized here in the test slide. There are communication latency, coordination complexity, the framework support to do this parallelism, and the stability when scaling to maybe hundreds of thousands of nodes. Okay. So we ran a lot of experiments, and we find that scaling not always yield better performance. So my idea to this presentation is to explain what we learned from this month running where we ran training of large language models in the Mare Nostrum 5. Okay, we found that the scalability was not linear as we increased the number of GPUs. As you can see here in this chart, once we went from 128 to 192, the scalability was much worse than with less nodes. Okay, so we found some solutions to this scalability problem, and after that we are ready to release the first models for Spanish, Catalan, and Basque, and other languages from Europe. Trying with the Mare Nostrum 5, we plan to release the 2B and the 7B models this Friday, and we are also trying the 40B model that we are training right now with 256 nodes by December. Okay, so this was the roadmap. We did that debugging phase. We ensured the correct operations, that's checkpointing, resumming of training, performing testing, scalability, and we are now evaluating and preparing the release of this model. So I went really fast, sorry, but we are quite late. So now I will summarize what I think it's there are the key takeaways for you for a more efficient use of Storm 5. Okay, so first, bear in mind the specific use of each queue. It is not, if you are only using CPU, please don't send jobs to the accelerated partition. This is very common. Also, do not run compute-intensive jobs in a login node because you can overload it, and then you can't even open a single document, a text document with Beam, because there is someone running jobs in the login node. Also, do not send a job to the queue asking for more nodes or more duration than the one you need for your job, because otherwise you are blocking the queue. Okay, Slurm tries to fit your job in a window. If you request for 2 days and you only need 2 hours, you are not using the queue properly. Okay. Also for short jobs, you can use the debug queue, and please do not abuse SIOC. Okay, to allocate a node or more. Okay. Also, I recommend to edit your bash file to set a new mask to ensure that you create the new files with the right permission. Also, as I think Laura explained, we have also a wall time. So if you need to move large files, please use data transfer copy, data transfer move, and data rsync commands. Okay, these commands are available only in data transfer nodes, but you can also load the transfer module from other machines, but this is not recommended. Okay. Also, please use symbolic links to avoid duplicating unnecessary data. And we have also local disks in each of the nodes. So if you need to increase your loading speed, you can, at the beginning of your job, you can copy your data to the local disk and then read your data from there. It's much faster. Speaking of file system, we have different file systems that are home, project, scratch, and tapes. And home is for your personal files, project is for the project data, environments, and final results, and Scratch is for temporal files, such as checkpoints or intermediate data. So don't do checkpointing in project because this is not intended for that, okay? And now I'm going to tell you some tips or some useful commands from Slurm. I think someone commented them, but I'm going really fast here. Batch to submit a job, the queue for view the job information, is cancel to cancel, and SIOC to allocate nodes to work interactively. Piece of vacation, and do not forget to release the nodes after you finish your work. Okay. Also, useful bash commands, htop to process monitoring. This was really useful for us to increase our performance. NVIDIA SMI to monitor the GPUs, and the other commands you can see here. Screen is also really good, so you can resume your job from another terminal. Okay. And we have also Mare Nostrum specific commands, such as BSC quota, to see the available space on each of the file systems. Check this regularly so you can run your experiments without the risk of this execution consuming all the space, because if this happens, the execution will stop. Okay. Also, you have used BSC queues to see the information of the queues that you have access, and select the appropriate one based on the number of nodes you need and the maximum duration of your job. I also recommend creating aliases in your bash for those commands that you use very commonly. I have here ones of that I use. It's the one, the SIOC node, and this I have this print dir structure that I don't want to write each time. Okay. Also good to know for the Storm 5 is that a daily backup is made only for the project system. This is why you don't need to do the checkpointing in this file system. If you accidentally delete something, you can contact the support team and they can recover these files for you. Also, in Milestone 5, we have 4 login nodes, and login 4 has internet access. You need to be at BSC or you need to connect by VPN. And this is really nice because you can install, doing pip install, for instance, other packages, and then you can run the execution for a compile node. Also interesting is to visit the HPC portal for job monitoring and to see the machine stats. And you can share your job with other members of your team, so they can also see your jobs. Okay. Now tips for scaling. In our case, everything was working, and then we tried to scale. Everything stopped working. What's causing the problem? We have these usual suspects. Is your parallelization correct? I'm not going to speak about parallelization in this talk, but in our case, we saw that some CPUs were saturated. So in that case, you need to assign the CPU affinity manually. To do this, you can use htop, for instance, to check the CPU usage. In the case of the storage, our file system was not loading the necessary data fast enough. We don't have a fast partition like Leonardo, so we try to move all the data to the local hard drives, and we created a virtual hard drive using all the local hard drive of the nodes of the job. And finally, we thought that the InfiniBand network might be saturated. So we assigned each of the InfiniBand lines to each of the GPUs, so they don't try to go all the GPUs to the same line. And finally, I think someone already explained about dependency. This is really important because this training was very long and I had to go on vacations. So I told an engineer to monitor the. And the first day I was on vacations, I got this email: you are blocking the queue. Having a second job in the queue is useful. So when the first fails, the second will automatically resume the execution. In this case, the problem was that the second job was not dependent on the first. And the problem too, that we were using 512 nodes for each of the tasks. So since we have the highest priority, Slurm was trying to reserve another 500 nodes for the second job, and it was blocking all the queue of the Milestone 5. So the solution is to submit the jobs always with dependency. I assume here some of them. After is to start all the jobs at once. After any is to so the dependency job begins once the previous one has finished. In any case, this is useful for not using too many nodes, as the previous example. After not OK is useful for resuming jobs from previous checkpoints. And for instance, the after OK is useful to run a second step. For instance, if you want to fine tune, you only do this if the previous execution was successful, or if you want to run an evaluation, you run only if the fine tuning job has finished with exit code 0. Okay. And I think this is the most important tip. Please read the Milestone 5 documentation. It's very complete. And also the support team at BSC is very competent. So if something is not covered by the guide, please contact them because they will help you with any issue.
Thank you very much, Aitor. And you are the last speaker of today's workshop. I think it has been 4 hours now that we all managed to sit in front of our screens, but it was very useful workshop, at least for me, to see all these tips and tricks and also to learn all the possible improvements that can still happen to help AI users on HPC. We are out of time, so our QA session will be very short, I think, especially you had the possibility to put your questions in the chat, and you still have during the coming few minutes, please pose your questions in the chat and we'll still try to answer. One thing I wanted to ask to our participants is the following. Now, you know, as Vangelis presented, we are to procure AI factories, and the AI factories intend to gather all the support across the Europe under the one roof, as well as to boost the hardware by procuring new systems or upgrades. And in this context, I have tried to note some things you have already said, such as the internet access from the nodes, the large RAM, the flash drive quick access, network, I don't know, long queues that were a bottleneck, not failing that were bottleneck, the library dependencies and also job dependencies. I would like to ask our participants, can you say just one thing each that we would need to consider when now procuring the AI factories? One, the most important thing for you. Any volunteers? And also the audience is welcome to put that in the chat. So what should we consider? Okay, we see the first one from Sampo. Anyone else? And the speakers are welcome to put or to say out loud. So one thing that we financing bodies, policymakers, and also our hosting entities need, or future applicants need to consider. Yeah, I see actually people joining while we're finishing. Large NV-link domains. Anyone else? You have the last few minutes. So access to uninterrupted compute. Diversity in hardware, not only GPUs. That's interesting. Hopefully there will be a diversity in Europe so that we can deploy this as well. And by the way, I invite you to also read in detail the call text of AI factories, which is online. I have posted some links previously in the chat. And you can see that we are also trying to boost the diversity, giving a possibility for some experimental hardware in the call. Anyone else? Last minute. Well, feel free to post more. And it's very important. This will be really considered in the evaluations and also by our hosting entities when and other applicants, I think, when applying. So and with this, I would like to thank all of you for really great presentations. I am going to watch this movie several times to learn a lot about AI on HPC. And you are always welcome to contact us through our info mailing list, and feel free to give your feedback after this event, how we can improve it. Thank you very much. And again, thank you to our hosting entities and users for these presentations. And have a nice day further. Bye.
You too. Bye-bye.
Bye. Have a nice day.
Bye.